Okay, 1560 crew. So you guys have the privilege of being with me while I record the first video for all the courses to wrap up chapter 15. So bear with me if there are some technology issues. What you should be seeing on your screen is an overlay of the slides so that you can see exactly what you're supposed to be looking at as I talk about them, which are also appearing over my shoulder so I can refer to them. And then I will appear somewhere on your screen as well. Hopefully it's just a tiny little square. So we didn't have too much that was left to cover in chapter 15. That's the good news. So we'll have a lot of time to finish up this chapter. That's what next week is going to be dedicated to, or this week, depending on what time you're viewing this video, because I'll expect you to need a little bit of time to catch up with what we looked at already. KSP and discussing solubility, Lewis acids and bases, and then where we left off after our last lecture was discussing the last type of equilibria, which were beginning to be introduced. And those last two equilibria, okay, which we see here on this screen, Kf and Kd, okay, those are the final two that we will have for this course, is how the solubility information and the Lewis acid and base information come together. As we were looking at those Lewis acids and bases, the product, when they came together, was called the Lewis acid-base adduct. And we can consider how stable this species is with what's known as the formation constant you see here on the top, Kf. Okay? And the inverse of Kf, right? So flip it around, flip the reaction around. The inverse of Kf is what's described at the bottom, right? Kd. F is formation, D is for dissociation. And that's the same thing like acid and base, Ka and Kb. If something's acting as an acid, you should be looking at a Ka. If it's acting as a base, you should be looking at a Kb. If a complex ion is being formed, you should be using the Kf. If the complex ion is the reactant and it's decomposing, you should be using the Kd. But as long as you have that in mind, the middle bullet point there, you're still determining these equilibrium constants like you would any other K value, right? It's still, just look at your reaction, put the products over the reactants, make sure you're paying attention to the coefficients, right? Because those would become superscripts in your K or your Q expressions. And then the only other bit of information, right, just like we discussed before with solubility, okay, a larger KSP means something, right, is more soluble. A larger KF now means something, some ion, a complex ion, is more stable. More of that thing would form in solution. So continuing to the next slide here, putting those ideas in action, right? We've got a reaction up top, the formation of copper cyanate, right? One copper comes together with two cyanide ions to form copper cyanate. Products over reactants, K if we are at equilibrium, Q if we are not at equilibrium. And then looking at these Kf values on this table here, right, that shows us that aluminum hexafluorate there, AlF6(3-), right, with the larger Kf value would be the most stable ion in solution. And just like KSPs, KFs or KDs would be given to you. Okay, you do not have to memorize those. On the next slide here, 43, with my numbers, the numbers might be a little bit off with the slides that are up on Blackboard. Okay, is a good practice problem, calculating the concentration of silver ion in a solution that's initially 0.1 molar AgNH3(2). And in that situation, okay, you can do this problem for practice. I'll use the document camera later on and write out how to solve this problem. What's shown on slide 44 here is just a general reaction scheme. Or I guess reaction scheme is not the best way to put it, a plan for solving these KF type problems. But it's just a different type of K, right? The theory behind it, okay, and how to do the math, ice tables, everything else is the same that we've been doing since chapter 13. So that wraps up 15.2. There's just a couple of slides that are contained within 15.3, and I alluded to this a couple times in chapter 13 and 14. If there are a couple situations where just considering one reaction, a single equilibria doesn't properly describe the system, and we saw that introduced in chapter 14 when we were talking about polyprotic acids, okay, things that can lose multiple protons. So all those species are contained within solution at the same time. Okay, so that's your definition of multiple equilibria. You get it right from the name, right? More than one equilibrium reaction is occurring simultaneously. And saw it with acid bases I just mentioned. Precipitation, it's introduced earlier in the slides, where the formation of a complex ion can affect the solubility of something else. What I use to introduce this idea shown here on slide 46 is what's happening with our oceans. Okay? Everybody's hopefully familiar with this. Right? We have in the top reaction gaseous CO2, right, being produced by industry. That's in equilibrium with aqueous CO2, getting dissolved in water in oceans, lakes, streams, etc. That aqueous CO2 can come together with water to form carbonic acid. That's what's shown on the second slide. Okay, and then that carbonic acid can act as a diprotic acid. It can lose one proton, that's shown in the third line, okay, to form H plus and HCO3 minus. HCO3 minus is the conjugate base of H2CO3, but it can lose another proton, right, acting as an acid again. That's what's shown on the bottom line, and then finally forming carbonate. So you see in that situation, right, we've taken CO2 from the atmosphere, which doesn't have any protons with it, but then indirectly introduced 2 additional protons to seawater, making it more acidic. Okay. So we talked about how acidity, right, is a bad thing. Everybody's familiar with that, coral bleaching, etc. And you can see how that can affect carbonate as well. As we're acidifying the oceans, right, not only is that having a negative effect on marine life, but it can also affect the solubility of carbonate, right, specifically calcium carbonate, which is the active ingredient, for lack of a better word, in coral reefs. Right? These coral reefs are made out of calcium carbonate. As the oceans become more acidic, then we're dropping down the carbonate levels because it's coming together with H+. Okay? That's driving the KSP forward, right, for calcium carbonate. So I'm not sure if you'll be able to see this, right? I'll put it up on the chalkboard over here. You got CaCO3 as a solid in equilibrium with Ca2+, which is aqueous, and CO3 2-, also aqueous. So as we drive that concentration of carbonate, CO3 2-, down, that drives the reaction overall to the right. And that's just a basic crash course on multiple equilibrium and how ocean acidification is hurting marine life and coral reefs. Jumping to the next slide, okay, we see the same type of reactions with calcium phosphate minerals. And now we're thinking about acidity, but now going to this slide, in our mouths. Okay. And the reaction that's up top there shows the decomposition of hydroxylapatite into calcium and phosphate and hydroxide. Okay. And obviously, as things become more acidic in our mouths, be it from drinking acidic drinks or just from the bacteria in your mouth that naturally produce some acids, that can lead to the decomposition of hydroxylapatite in your tooth, right? That's what tooth decay is all about if you don't brush your teeth. Okay? But if we look at this next slide here, number 50 on my slide numbers, if we introduce some fluoride, we convert hydroxylapatite to fluoroapatite. That's what's shown on the product side over there with the fluorine, the calcium, and the phosphate all together, which is less soluble than your natural tooth enamel. Right? Which is not to say that you should just grab some fluoride out of the lab and start chugging it. Right? You want fluoride levels to be extremely moderate, less than like 4 ppm, a really low concentration. Because if you get too high of a concentration of fluoride, that can have a negative effect on your bones. So we wrap up the chapter with a discussion of dissolution, right, your KD versus weak electrolyte formation. And these last 2 slides, 51 and 52 here, discuss how we have multiple equilibria interacting with one another. Okay? We've got something that's slightly soluble, okay, but with a common ion effect. Now, as we were discussing before, right, the formation of a weak or a complex ion, or the dissolution of a complex ion, can affect that equilibria as well. So we've got KSPs. If we're dealing with the acidity or basicity of a solution, we might have a Ka, a Kb, and we've got Kfs and Kds that can all come together. Okay. So there's 2 final slides to kind of review all these ideas. This is slide 52, example 15.16. And this is something we'll talk about here in a second, but I'm going to jump forward and then come back to it. This capstone example, 15.15, right, is putting all those multiple equilibria together, KF and KSP. I'm also going to upload a slide where I show how this problem is solved, but it takes up like a whole page. It's an extremely difficult example, and that's why I've called it a capstone, because it ties together a lot of chapters all at the same time. That is harder than anything you would expect on a quiz or a test moving forward, just so you know. Okay, so look for that video to be uploaded later on. Okay, but I want to come back now to this example 15.16, asking what's the effect on the amount of solid nickel carbonate that dissolves on the concentrations of nickel and carbonate, right, when we see those changes that are listed in A through E. And this is in your textbook, but for practice, what you should do, right, is pause the video now and think about it in each situation, okay, A through E. What's going to happen if I'm thinking about the reaction of nickel carbonate to form Ni2 plus and CO3 2 minus in solution? So this is a KSP problem, right? Nickel carbonate as a solid as the reactant, Ni2 plus and CO3 2 minus, aqueous as the products. Okay? And we're thinking about the common ion effect. So pause now, think about those, and then unpause, and I'll talk about them in each situation. Okay. A, if we're putting in nickel nitrate, okay, what's going to happen to nickel carbonate? Okay, well, that's the common ion. If I'm trying to dissolve nickel carbonate, okay, nickel nitrate is fully soluble, so I'm indirectly putting nickel 2 plus into the solution. Okay, so that means overall less of the nickel carbonate is going to dissolve. Now B and C, okay, oh, sorry, I was getting ahead of myself. It's actually B only, because the other two have different effects, right? Looking at B, potassium perchlorate, fully soluble because it's got a group 1 ion and a perchlorate, but neither of those ions are involved in my equilibrium, so that doesn't have an effect on anything. Okay. C, nickel carbonate, solid. If I put that into the solution, does that mean more or less is going to dissolve? No, my solution's already saturated. So if I'm adding in the solid, which keep in mind, this would appear in the KSP expression as a solid, that would have no effect on the equilibrium. Okay. Looking at D now, potassium carbonate, same type of idea as A, right? Putting in potassium carbonate, which is fully soluble, increases my concentration of carbonate in solution, which means overall less nickel carbonate dissolves. Again, the common ion effect. Okay. And then the trickiest one, E, adding in nitric acid, HNO3. This kind of relates to the equilibria we just saw talking about ocean acidification. Right? If we have an acidic solution, now some of those H pluses will come together with CO3 2 minus, right, to form HCO3 minus, which means if I'm adding in nitric acid, what I'm indirectly doing is lowering the carbonate concentration. Okay? That means that more of my solid nickel carbonate can dissolve. Okay? So to summarize those situations, A, less nickel carbonate dissolves. B and C, no effect, but for different reasons. And D, less nickel carbonate dissolves. And E, more nickel carbonate dissolves. Those are the type of questions from KSP, the common ion effect, in addition to others that you can expect on the Chapter 15 quiz. So if you have any questions, right, remember we've got that practice problem and then 2 other videos you're looking for those examples to be uploaded as I write them out. Okay, just make sure that those are on your radar. Any questions, shoot me an email, post on the Blackboard discussion. You will be expected to post twice for Chapter 15 if you aren't connecting with me via Zoom. Okay, and we can discuss these in review, office hours, etc. Okay, as well as for anything we covered in lecture prior, feel free to ask.